Hello, this is Mr. P, and today we're going to learn about the trigonometric form of a complex number. We're going to start with the complex plane, which is also called the Argand plane, and that happens when we have the real axis, which we used to know as the number line. Any real number would be somewhere on this number line. That's our x-axis or our real axis. And then the vertical axis is going to be our imaginary axis. So to find any complex number, there's going to be a real component and an imaginary component. So z, for example, represents a complex number. It's going to be x plus yi. There's two ways to look at this coordinate, though. We can look at it in the rectangular form, which is what we just did. That's where we get to the point by going horizontally and vertically. So we can describe the position of this point on the plane as x is the horizontal distance, y is the vertical distance, so it's x plus yi. The other way we can look at this is what's known as the trigonometric form, or that's also known as the polar form. For the polar form, rather than looking at the sides of this triangle, we find an angle and then go directly to it in that direction. So that would look something like this. That same point z, instead of describing it in terms of x and y, we're going to look at this angle theta that the hypotenuse of this triangle would make with the real axis, and then r would be the length of that hypotenuse, or the radius of the circle that contained z. So you see here, z can be either x plus yi, or we're going to see in a second why, it's r times cosine theta plus I sine theta. And when we talk about the trigonometric form or the polar form of complex numbers, we do want to restrict our radius to a positive number, or actually a non-negative number. It can be greater than or equal to 0. And we want to have our theta between 0 and 2 pi, or for degrees, 0 and 360 degrees. So let's start out with some definitions. We're first going to look at the magnitude or modulus of a complex number. That is simply going to be the length of that hypotenuse in that last diagram we saw. We want to think of magnitude or absolute value as the same as we would on the real number line. Absolute value is the distance from 0 on a number line. Well, in the complex plane, it still has that idea of distance. It would simply be the distance the point is from the origin on the complex plane. So in our last diagram, that would simply be the length of that hypotenuse. So we can see here z, or the absolute value of z, is going to be the square root of x squared plus y squared, which makes this the hypotenuse of that triangle, and we're going to call that r for the radius. Also, to refresh your memory, the conjugate of z, because we'll run into those as well, the conjugate of z, and then we use the notation z bar, that's z with a little line above it, that is going to be equal to x minus yi. To find the conjugate of x plus yi, you simply change the sign of the vertical component. Now, when we talk about polar form, and we're going to see how we got to that r cosine theta plus I sine theta, again, our radius must be non-negative, and theta is between 0 and 2 pi, or between 0 and 360. So if we have a complex number, x plus yi, then the polar form, we can think of it this way. We saw the triangle where the r was the hypotenuse, and x and y were the legs of the triangle, of a right triangle. So if we remember from trigonometry that x, which would be with respect to theta, that is, would be the adjacent side of any triangle you can find by multiplying the hypotenuse, which is r, times the cosine of the angle. So that would be x. Likewise, your y, which is the opposite side in a right triangle, is going to be the hypotenuse times the sine of the angle. So if we take this expression, we factor out r, then it's simply r times cosine theta plus I sine theta. And this even has a alternative notation that you don't actually find in too many textbooks anymore. Although mathematicians still use it, you rarely see it in the textbooks. And the alternative notation is cis theta. where CIS stands for cosine plus I sine. So this formula here can also be written as r cis theta. It's a quicker and easier notation. Also notice how we have magnitude and direction, so this is going to act as a vector as well, and we'll see more on that later. Alright, so let's look at some examples. Let's see what we need to be able to do with these. Let's say that we're asked to plot this point, which is z equals square root of 3 minus I, and then we also want to convert it to polar form. Right now it's in rectangular form. We're going to convert it to polar form. Well, plotting the point is fairly straightforward. We're going in the positive direction horizontally and then the negative direction vertically. So we're going plus square root of 3 and then minus 1 gives us the point right there. And to convert it to polar form, there are two things we need. We need the radius and we need the theta. We need the angle. Now the radius, there is a formula for the radius, which is the square root of x squared plus y squared. And we can simply substitute it in the numbers and work the algebra and get to 2. There's also a visual approach which will pay off in the long run if you can approach these problems more visually. And the visual approach is taking the point we have here, or thinking that as a triangle, we went square root of 3 and then we went minus 1 to arrive at that point. So those two numbers are really the sides of a right triangle, and the r is going to be this hypotenuse. Now, hopefully you recognize these numbers as 1, 2, square root of 3, which is a 30, 60, 90 triangle. So therefore our radius would be 2, which is the same number we got here, but we didn't have to do all those calculations. And for the theta, again, you can do it algebraically. You can say, well, theta, the sine of theta is going to be y over r, so sine of theta is negative 1/2. Cosine of theta is x over r, so that's root 3 over 2, and our theta must be between 0 and 2 pi. And then you can take the arc sine of both sides, take the arc cosine of both sides, and make sure that solution is within 0 to 2 pi, is in the correct quadrant that it's supposed to be in. Or you can look at it again visually. Notice how this was a 30, 60, 90 triangle, and 1 is the shorter side of the two legs. It's the shorter leg, so this will be the smaller angle, so this will be the 30-degree angle, which in radians is pi over 6. So the angle we want is actually the entire angle. This is the angle we're looking for. If I know this is pi over 6, then this red angle would be all of 2 pi minus that pi over 6. So 12 pi over 6 minus 1 pi over 6 would be 11 pi over 6. So whether you take inverse sine and inverse cosine of both sides, or whether you do it visually, you should get that theta is 11 pi over 6. Our radius is 2. So in polar form, we're using this form here. It's simply going to be 2 times cosine 11 pi over 6 plus I sine 11 pi over 6. Or using the more efficient notation, we would just write it as 2 cis 11 pi over 6, which I think is the easier way to write it, because all you need is the radius, the angle, and you can go right to this form. Alright, so this was going from rectangular to polar. Let's look at what happens when we go the other way. This time we're given our complex number in in polar form, and they want us to rewrite it in rectangular form. Well, for that, we're simply going to, first of all, I will show you the visualization. This is what it would look like. But to calculate this, it's really just algebraic. You sort of just have to evaluate what is the cosine of 30, what is the sine of 30, and just multiply it out. That's really the quickest way. So if we look at 2 cis 30, and we do want to have the expanded notation, the cosine of 30 is square root of 3 over 2. The sine of 30 is 1/2. Hopefully you should know those by now. And then we're simply going to distribute the 2 so that the 2's cancel, and you're going to get square root of 3 plus I. So going from the polar back to the rectangular is actually very easy, especially if you're able to do these ones in your head. 30 degrees, 60 degrees, 45 degrees, those you should be able to do in your head. Alright, let's look at some other advantages of polar form. We can take shortcuts when we either multiply or divide complex numbers. Now, here's the official definition of it. The magnitude of the product is going to be the product of their magnitudes, and the argument of the product is going to be the sum of the arguments. And the same holds for quotients. The magnitude of the quotient is the quotient of the magnitudes, and the argument of the quotient is the difference of the arguments. And these are the corresponding equations, but a much easier way to think of it, I believe, rather than trying to memorize the equation, is to actually think about it in terms of the words, where if you're going to multiply two complex numbers, you simply multiply the magnitudes and add the angles. So z1 times z2, you're multiplying their respective radii, or their magnitudes, and you're simply adding the angles together. When you're doing division, you divide the magnitudes and you subtract the angle. So just like the laws of exponents or the logarithmic rules, notice how multiplication is associated with addition and division is associated with subtraction. All right, so let's see some examples of these, of course. All right, we're given these two numbers, z and w. Z is 3 cis 20, and w is 5 cis 100. And they want the product, and they want the quotient. So again, reminding you of our formulas here. I'm going to use the cis notation to make it a little quicker and easier. So for the first one, I'm multiplying two numbers. This first one was 3 cis 20. Second one was 5 cis 100. And all I do is multiply the magnitudes. 3 times 5 is 15. Add the angles. 100 plus 20 is 120. And that's my answer. Pretty straightforward, pretty easy. When dividing, it's pretty much the same process. I'm going to use the cis notation because I prefer that. So again, it was 3 cis 20 is z, and 5 cis 100 is your w. So we're simply going to divide the numbers, which gives me 3/5, and then 20 minus 100 is going to be a negative 80. Now, this is the point where getting here was straightforward, but now you have to remember that we do have restrictions on our polar form. We want our magnitudes to be positive, we want the radius to be positive, and we want this angle to be between 0 and 360, or 0 and 2 pi if you're dealing in radians. So here, if we want a coterminal angle to a negative 80 degree angle. Well, if you remember, we can add or subtract multiples of 360 and the angles will be coterminal, so you simply add 360 to this number and you're going to get an equivalent angle, which is 280 degrees. So our final answer is 3/5 cis 280. And remember, cis is cosine plus I sine. Okay, let's look at how we can further expand these ideas into what's called de Moivre's theorem. And I know a lot of people mispronounce this the first time they see it, but the correct pronunciation is de Moivre's theorem. And this says that if we wanted to raise a complex number to a power, then we can do a little shortcut formula as long as we're in polar form. Then z being our complex number here, z to the nth power, we're simply going to take the radius, or the magnitude, and raise that to the n, and we're going to multiply the angle by the n, which makes it a nice, quick, and easy shortcut. Now, of course, we want to see an example of this, so let's go to our problem. Let's say we're asked to write 1 plus I quantity to the 5th in standard form. Of course, the first way is you could multiply it out, just distribute it 5 times. Or you can use the binomial theorem, if you remember that as well, and work the algebra and get to it. But we're going to take more of a visual problem to use de Moivre's theorem. In order to use the theorem, or to use the formula, notice this is our formula, we need to know 4 different things. We need to know z, r, n, and theta. Now z is simply the number that we're raising to a power, so that's 1 plus I. N is the exponent we're raising that number to, so n is going to be 5. And then for 1 plus I, we can think of this as our visualization as 1 plus I on the complex plane. 1 in the horizontal direction, 1 in the vertical direction. And hopefully you recognize a 1, 1 square root of 2 triangle, which is a 45, 45, 90. So that means our radius would be the square root of 2. And then our angle, since we recognize the 45, 45, 90, our angle is going to be 45 degrees, which we're going to use radians in this problem, which would be pi over 4. Normally, in problems, you use radians unless the problem itself has degrees or asks for degrees. Remember, radian measure is the default measure of an angle in mathematics. All right, so here we have 1 plus I to the 5th, and substituting into the formula, we're going to take our radius and raise it to the 5th power, so it'd be square root of 2 to the 5th, and then we're going to take our theta and multiply it by the n, so 5 times pi over 4 is 5 pi over 4. And now we want to clean this up a little bit because they did ask for it in a plus bi format. They do want rectangular form. So for the radius, it's the square root of 2 to the 5th power. The way you can think of that is the square root of 2 squared would be 2. So if I have squared squared, in other words the 4th power, that would be 2 times 2, which is 4. So the square root of 2 to the 5th would be the square root of 2 to the 4th times the square root of 2. So it's simply going to be 4 root 2. And then for the cosine and the I sine, first of all, I want the cosine of 5 pi over 4. Well, again, we can think of that visually. 5 pi over 4 is pi over 4 more than pi. So this would be pi plus another 1/4. Makes this a 45, 45, 90 triangle. So it's 1, 1 square root of 2. Don't forget the negative signs for your direction because it's left and down. The hypotenuse is always going to be positive, but your legs do have directional components to them. So if we think of this as our visualization, then the cosine of this angle is simply going to be the adjacent over the hypotenuse, which is negative 1 over the square root of 2. And then the sine is going to be also negative 1 over the square root of 2, which is opposite over hypotenuse. And now it's just a matter of distributing. When you distribute, the square root of 2's cancel out, which make it nice and easy. So it'll be negative 4 minus 4i. And don't forget to pay attention to these negatives. Alright, along with raising to a power, we can also take complex roots. So let's look at our procedure for that. So finding complex roots, if we have a number, and we're going to use w this time to be the number we're going to take the root of, that's r cis theta, then we can take the complex roots, and depending on which root we're taking, and by the way, this only applies to integer roots that are 2 or more, so square root, cube root, fourth root, etc. However many roots we're taking, that's how many, or whichever root base we're taking. So if I'm taking the cube root, I will have 3 answers. Taking the 7th root, I'll have 7 answers. So there are going to be actually 7 different answers here if I'm taking the 7th root, and that's what this k represents. So using this formula, we notice that, and it works right along with de Moivre's theorem, instead of raising the radius to a power, you're taking the root of the power. And instead of multiplying the angle, you're dividing the angle. The only difference on this one is, notice it does have the 2k pi because it is cyclical. Because, like we said, depending on which root you're taking, you're going to have that many of them. And we'll say a little bit more about the spacing on this in a second. Alright, so let's go ahead and jump into a problem here. We're asked to find the complex cube roots of negative 1 plus root 3i. And they want us to leave the answer in polar form with our argument in degrees. Alright, so again, just refreshing your memory on the formula here. We want to know three things in order to be able to use this formula. I want to know what is n, r, and theta. Now the n, I get right from the problem. Notice how they want the complex cube roots, so they want n is equal to 3. If they wanted the square roots, n would be 2, and you just get it from which root you're taking. Now, for the radius and the theta, we can look at this visually. Again, here is -1 plus square root of 3i would be -1 in this direction plus square root of 3i in this direction. And hopefully you recognize the 1, 2 square root of 3 triangle, which is your 30, 60, 90 triangle. So our radius is obviously going to be 2. And since this is a 30, 60, 90 triangle, and square root of 3 is the longer of the two legs, which means this is the larger of the two angles, so this is a 60-degree angle. And they did ask us for degrees, so this is a 60-degree angle, which makes the actual angle, that's the reference angle, by the way, is 60 degrees. So the actual angle would be 120. All right, now it's just a matter of substituting into the formula. So we're going to have three answers. We call them Z0, Z1, and Z2. And for the nth root of r, we're simply taking the cube root of 2, which would give us that number. And then it's going to be cis, of course. And then we want the theta, which is 120 degrees. Theta divided by your n. And so 120 divided by 3 is going to be 40. But also notice this is our first one. Our initial root is when k equals 0. So if I plug 0 in here, this goes away. I don't even have to worry about it. And I simply have 120 over 3, which is 40 degrees. Plugging in the 1 for the k, and then the n and the r, you notice how I'll have, again, the cube root of 2. Again, I'll have the cis. This time we have theta is going to be the same 120 we're starting with. So theta divided by the n, we're starting with the 40, but we're adding to it. And I know the formula is in terms of pi, but we're working in degrees, so it's actually going to be 360 times k, because 2 pi is 360 degrees. So 360k, we're simply going to divide the 360 by the n, which is 3, so that's going to be another 120 we're going to add to it. So if we add that 120, we're going to get 60 degrees. Or you can just plug the numbers in and do the algebra, and you're going to see you get 160 degrees. Now notice how for the magnitude, it doesn't matter which root you have, that radius, that magnitude is going to be the same, because these are not dependent on the k. The k is what differentiates this answer from this answer from this answer. So for all of these, they're going to be square root of 3 over 2, so you're going to have the same radius for all of your answers. That's an important thing to realize. Likewise, they're all going to be cis. And then that same difference here, notice how I have our theta divided by the n. That initial angle doesn't change. And then the n, I have 360k divided by the n. The 360 over n ratio, which is 120, that doesn't change. The only thing that's going to change is k, how many of those we have. So really, if we add another 120 degrees, we're going to have our next answer, which is 280. And again, the reason these are 120 degrees is because you think of this as the full circle, 360 degrees. Remember, 2 pi is 360 degrees. If we divide that by n, that's 120 degrees. And then you're going to multiply that 120 by 0. Then you can multiply that 120 by 1. And you can multiply that 120 by 2. So we can see that these are all going to be evenly spaced, which is a very important thing to recognize. Because in reality now, once you know this, all you really have to do is figure out the first one, which when k is 0, you don't even have to worry about that at all. So figure out the first one, and then these are all evenly spaced, and these are all the same. You can just go right down the list and find the rest of them. All right, now if we look at this visually, I said that they are all evenly spaced. Let's see the visualization of these three solutions here. Notice how we're on the complex plane. I know there's a lot of information on here, but we're on the complex plane. The radius was simply that cube root of 2. And then we have our first answer was 40 degrees along the circle that has a radius of cube root of 2 in the complex plane. So this was our first answer. And then 120 degrees more, same radius, but 120 degrees more puts it at 160 degree angle. And then the last answer was same radius, 120 degrees more, puts it at 280. So your complex roots will always be evenly spaced. One other thing that you could recognize, and it's pretty easy to prove, is that if you think of these three solutions as vectors, you could move these vectors. Matter of fact, let's do this. You could move these vectors, since they are all evenly spaced. You could always take these vectors and create, if you go nose to tail, you can always create a polygon, a regular polygon of n sides. And this tells us that, because remember, complex numbers are vectors, this tells us that the sum of all of your complex roots is always going to be 0. Because notice how no matter where you start, if you follow along all the vectors, you end up at the same spot. So that's easy to prove that the sum of all the complex roots, no matter how many of them you have, if I'm taking the 17th root of 87 in complex numbers, all of those 17 roots, if we add them together, are going to equal 0. And that actually brings us to what we call crossover tactics. These are more advanced ideas. You're not going to necessarily need them in your homework on this section, but these are things to think of for solving problems down the road. And the reason that the complex plane is so fruitful when solving problems is because they have multiple meanings. So what we mean by crossover tactics in mathematics is we'll take a problem that might be algebraic and we'll change it to a geometry problem, and we can solve it easily using geometry, and then we'll transform it back to algebra at the end. So it's taking it from one discipline of math into another discipline so you can work the problem easier and then interpret the results back into the original discipline that the problem was written in. So with complex numbers, the great thing about them is they are both algebraic and geometric. You know, they represent the x plus yi, and they also represent the legs of the right triangle. And then in addition, the complex numbers are simultaneously points. They're points on the plane. They're vectors because they have magnitude and direction. And they can be thought of as geometric transformations as well. So that gives us a lot of latitude or a lot of ability to look at things differently. Conjugation, we talked about conjugation. The geometric interpretation of that is conjugating is just a reflection of the complex numbers, Z is our complex number, in the real axis. So if we saw that in one of our examples. If we had x plus yi, then the conjugate x minus yi is just going to be a reflection vertically. Also adding and subtracting, and we touched on this, since complex numbers are vectors, that means addition or subtraction of complex numbers obeys the parallelogram rule of vectors. And we just saw that led to all of the roots, complex roots, summing up to 0. Next we have multiplication. If you multiply by I, which is the imaginary unit, then geometrically that would be the same as rotating by pi over 2 or 90 degrees counterclockwise. And think about it as a real number. Let's take the number 2 for example. Think about where 2 is on the complex plane along the real axis. If I multiply that number by 2, that number now becomes 2i, which would be 2 units straight up. which is a rotation of that vector from 0 to 2 in the real number line. You rotate that vector through the origin, about the origin. You rotate that vector pi over 2 radians counterclockwise, and you'll get a vertical vector, which is 2I. And that works for any vector or any complex number. Also remember that multiplication by a being just a number, geometrically that means you take that vector and expand it by a factor of a. It's the same idea as a scalar times a vector, because the complex numbers are vectors, so if we multiply it by just some scalar, then that's going to be expanding that vector by a factor of a. Multiply by 2, you double the length. Multiply by 3, you triple the length, etc. And also very helpful in solving problems to know that the complex roots are spaced evenly on a circle in the complex plane. That circle is going to have the radius, which is the nth root of that first complex numbers radius, and then all of those solutions are going to be evenly spaced on the complex plane. And then we saw by a little demonstration, we didn't quite rigorously prove it, but by a little demonstration we saw that the sum of the nth complex roots is always going to be 0 as well. Now again, these are a little more advanced thoughts to keep in mind as you go forward in math, but they can be great time savers in problem solving. For example, let's look at this problem here. You're getting to the point in mathematics where you have multiple tactics available for you to solve problems. So if we look at x cubed minus 8 equals 0, we have a polynomial equation, and we're asked to find all solutions to the equation. So all solutions means we want to solve this over the complex plane. So our first approach is in Algebra 2, for example, our approach would be to factor the side if we can, factor the polynomial. And this can be factored if you remember your difference of cubes, because the 2 cubed is 8, so you can think of this x cubed minus 2 cubed. So you could factor this as x minus 2, the quantity x minus 2, times x squared plus 2x plus 4. And then you'll see that then you set each factor equal to 0. I'm not showing this because this should be review. Set each factor equals 0, so one of your solutions would be 2, and the other solution, you would have a quadratic that doesn't factor over the integers, which means you could either use the quadratic formula or you can complete the square to find the other two factors. So you can do this algebraically with the stuff you learned in Algebra 2. Or you should have also learned when dealing with polynomials that you can use the rational root theorem to test for possible rational roots. So you look at the constant. It's factors of the constant over factors of the leading coefficient, which in this case is 1. So we could have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8 would be the 8 possible rational roots of this polynomial. And if you test them with synthetic division, you'll find that 2 works. And once you find one that works, that means you drop the degree of the problem by 1, so you'll now have a quadratic that remains. You'll find that none of the other potential roots work for that quadratic, so you'll have to again either use the quadratic formula or completing the square. So with that work, those are 2 ways that you could solve the problem. But I think a much more elegant way, now that you understand the complex plane, is to go ahead and since we don't have the square term or the linear term, it actually makes it very easy to add 8 to both sides and then take the cube root of both sides. Now, since we're taking the cube root, there are going to be 3 of them. Now, the first one is easy to see. The cube root of 8 is 2. That one's the easy one to see, but now we have 2 other roots that we need to figure out. And we can use all the stuff we just realized in the crossover tactics to quickly and easily figure those out. So first of all, we're going to have the complex plane. Think of the complex plane. We know one of our answers is 2. Well, 2 is a complex number. It would be 2 plus 0i. So if we put 2 plus 0i on this plane, let's say that this vector here represents 2 plus 0i, then that would be our solution, and this would be on a circle of radius 2 in the complex plane. Now our other two solutions, remember they're evenly spaced about the circle, so that means the 360 degrees divided by 3 is going to be 120. There's going to be 120 degrees between solutions. Interesting to note that anytime you're dealing with cube roots, it's always going to be 120 degrees, which makes them, if one of your answers is real on the real number line, then it's going to make these special right triangles that you can work with. Because if I go 120 degrees in this direction, I get this vector, which I already know has a magnitude of 2. And if this is 120, that makes this angle here, if I drop a perpendicular, this angle is going to be 60. So it makes a nice little 30, 60, 90, which hopefully you recognize as a 1, 2, square root of 3 triangle. Now don't forget that the legs do have directional components, so it's actually -1 and positive square root of 3 to get to this point. So in rectangular coordinates, -1, positive square root of 3, I. And that is our second root. Now we can continue on another 120 degrees and try to work out this triangle. But again, let's work smart rather than hard. If you remember that from the rational root theorem and from dealing with polynomials, that if you do have a root of your equation or a solution to your equation that is a complex root, then they always come in conjugate pairs. So if you have -1 plus 3i, you're going to have -1 minus 3i. And you can see again visually that this vector reflected about the real axis is going to be this vector, because that's what conjugates are geometrically. So here are 3 roots of the equation. And we're done.